Going to be a quick little clip to see how motion with drag shows up in both parts of AP Physics C. So in mechanics, it's typically something like a dropped object with air drag, and so when you first let the object go, we'll say we drop it from rest, you'd have mg, the weight, acting on it, and of course as it falls, mg is going to continue to act on it. But as it picks up speed, it's going to build up a bit of drag force. So if we go with a linear drag model, where drag is proportional to velocity, you'll have this force backwards that's BV. That grows as the ball falls and gains some speed. All right. Well, so if we go to look at how this thing moves, if the goal is to get the velocity as a function of time, we'll just start with F equals ma. So we say, okay, if I take F equals ma, since the ball's moving down, I'm just going to make positive beat downward. Then our forces on the ball would be mg down in the positive direction minus the drag equals m. And then I could write a here, but what I'm going to do is that will give me kind of too many variables if I'm going for v of t. So I'm just going to write a as dv by dt. So it's first derivative with respect to time and the velocity. And then what I want to do is solve for v. So different styles of this, just personal preference. I like to just clear the coefficient on it. So I'm going to divide through by minus b. So you'll get minus mg over b plus v equals minus m over b dv dt. And then I'm going to separate and integrate. And so what you do with this is, or what I'm going to do is move all this on the left, I'm going to put under the dv. So dv over all this, dv over v minus mg over b. And then everything else is going to come back on the left. So over here it's going to be minus b over m dt. So it's now separated. I can then integrate. So we'll go from when we start our stopwatch, time t equals 0, up to t. We'll go from where we start our velocity, which in this case is going to be v equals 0, up to some arbitrary v. This side's going to integrate to minus b over mt equals, and then this is going to be log of this expression, okay? So it's going to be log of v minus mg over b. But what you have to do is plug in the two limits. So it's going to be log of this thing with v plugged in as the limit. So it's going to be like log of v minus mg over b. Okay, and then minus log of this thing with 0 plugged in for v, right? So you could say, and so what's going to happen is if you have log of the thing with v plugged in minus log of the thing with 0 plugged in, if you remember, like log of a minus log of b is log a over b. That's the same thing as log a over b. Well, so what you can do with that is put this expression with v plugged in the numerator, and then that expression with 0 plugged in goes in the denominator. So this would be over minus mg over b. Okay, and then now all that's left is to solve for the velocity. So you'd exponentiate both sides. E to the minus b over mt equals this thing, v minus mg over b over minus mg over b. And then finally, all you'd have left is to solve for v. So finally, in all its glory, we get v of t equals, what you would do to solve for it is you would multiply by minus mg over b and then add mg over b. So we have our added mg over b minus mg over b times e to the minus b over mt. Right? So what this is, this function, that is your velocity as a function of time. What that is, or what that would look like, is an exponential approach to mg over b. So that function, if you graph it, here's mg over b, here's the velocity on this axis in time, is that function is going to look like this. It's an exponential approach to mg over b. The reason it approaches mg over b is when these forces balance, it stops accelerating. So you have these forces balancing, and you'd see the velocity when these forces balance is v is mg over b. So that's this thing approaching terminal velocity, just a dropped ball. If we go over onto the electricity and magnetism side, what's going to happen here is when we start to drop this, it's going to fall, but that's going to change the amount of flux that's through this loop, and current's going to start to go. Well, so what will happen is as this thing falls, we've seen previously that the induced EMF, or the voltage that's induced, is going to be BLV, right? That just comes from change in flux with time equals the voltage. And then we can say, well, V equals IR, and then that's going to let us solve for the current in the wire as it falls. So the current in this circuit is going to be BLV divided by the resistance. So as this thing falls, right, it's going to be losing inward flux. So it's going to try to make its own inward flux. So that current's going to go like this, right? You're going to have a magnetic force because you have a current running in the presence of a field. And so this upward magnetic force is going to be your magnetic force on the segment of wire. And that magnetic force is going to be BIL. BIL. Right? So if you do the similar thing and set up F equals MA, you'll say, okay, well, F, sum of the forces equals MA. Again, I'm going to choose positive down. And your force on the thing is going to be, you have mg pulling it down, mg pulling down this way, and then you have BIL pushing back up equals mdv dt. Well, what we can do is put in this expression for the current that we found, and you'll see it depends on velocity. So we have a velocity-dependent force here. So we have mg minus, now if you put all this stuff in for the current, you'll see that you get b squared L squared V divided by R equals mdv dt. Now what you notice when you get here is that this equation that's governing the velocity as this thing is falling, this looks exactly like what we got right here. So you have gravity making this thing want to go downward or in the positive direction. Then you have a force that's just proportional to velocity that's going back upward equals mdv dt. So same equations really, and so they'll have, well, the same solutions with some different constants. So I encourage you to walk through the rest of this to get the expression for the velocity as this thing falls. Again, assuming that it's staying in the field for a good while, so it can kind of approach terminal velocity. Walk through the rest of solving this differential equation in case anybody got stuck. I'll just do it over here to just so there's a little more space. Just going to recopy it real quick. So what you have is the force downward mg, accelerating it downward, and then resisting that falling downward is this drag force, b squared L squared V over R, and that equals mdv dt. So this is the differential equation we're trying to solve. We just need to separate the variables and integrate. My own style is I just like to clear the coefficient on the thing that I'm looking for. So what I'm going to do is divide everybody by by minus b squared L squared over R. And so what that's going to do is over here, that's going to make this term minus RMG over b squared L squared plus V equals, and then that's going to make this thing minus MR, or RM, I'll keep it that way, over b squared L squared dv dt. And so now we're ready to, I'm going to separate and integrate. So what I'm going to do is bring the entire left-hand side under the dv. So we've got dv over this mess. What is this? V minus RMG over b squared L squared. And then everything else is going to go over on the left. And so the everything else, I guess, is this stuff that I'm circling there. So all that junk needs to go on the left. So that's going to be minus b squared L squared over Rm dt. And so now we're set. We've got the thing successfully separated. And so now it's time to integrate. What we'll do is we'll go from where we start our stopwatch to some arbitrary time when we stop it. We'll go from, we'll drop it from rest to some arbitrary velocity. This side, simple integral, that's just a constant, so it's just integral dt. So that side will just integrate to minus b squared L squared over Rm, because that's just a constant. And you just have that integral d of dt, which just becomes t. Evaluated at t minus 0, which just gives you a t. And then this guy, this integral is just going to be natural log of this stuff that's in the bottom. So we'll get natural log of this stuff, v minus Rmg over b squared L squared. And then the key here, though, is you got to remember that you can't be lazy with the limits. So what you got to do is plug in the expression with that limit, and then minus the thing plugged in with that limit. Right. So you'll get minus b squared. I'm just rewriting this. L squared over Rm t equals. So it's going to be log of this expression with v plugged in. Well, that's identically this. So you get log of, and then it's going to be v minus Rmg over b squared L squared. Okay. Oh, and then we have to plug in at 0. So you could write this as log of this expression minus log of this expression with 0 plugged in, right? But log of a thing minus log of a thing is log of the first thing over the second thing. And so I'm just going to skip that line of algebra. And so what's going to go in the numerator here is this expression with 0 plugged in for the v. So down here you'll get minus Rmg over b squared L squared. Again, just in case I'm going too fast in the algebra, it would be log of this thing minus log of that thing, but log of one thing minus another thing gives you log of the first thing divided by the second. So it looks like this. And then the last move here is, well, we need to extract this v in order to solve for v of t. And so what you want to do is exponentiate both sides, or e it, as some of my students will say. So if we exponentiate this side, so new line over here, if we exponentiate this side, you get e to the minus this constant, let's see, b squared L squared over Rmt. So that's on that side, equaling, well, all this junk without the ln. So you get v minus Rmg over b squared L squared over that minus Rmg over b squared L squared. Whoops. And then final move now is just a little manipulation to solve for v. So to extract the v, so v of t, because it's going to be a time-dependent function with this, to get out v, what you have to do is multiply this term over and then add Rmg over b squared L squared. So, right, that last move is we had added Rmg over b squared L squared. And then minus, and then we'll have a term that's from this thing in the numerator multiplied by this exponential. So it'll be minus Rmg over b squared L squared, and then times that exponential factor, e to the minus b squared L squared over Rmt. T. And so that is supposed to be our velocity as a function of time. What that's going to look like is an approach to Rmg over b squared L squared. So velocity is going to tap out, right, when we get to t equals infinity, right? Then this would be like e to the minus a big number, which is 0. So this whole second term would be gone. And the velocity is just going to approach this Rmg over b squared L squared. To see why that is, is when it hits a terminal velocity, it's not going to be accelerating anymore. So this like right-hand side of the equation, the dv dt would be 0 if it's not accelerating anymore. And so if the acceleration is 0, then this term equals that term. Notice if you solve for v, given this being 0, then you would get, solving for v would give you rmg over b squared l squared. So this mass here is actually the terminal velocity that just comes from setting the net force equal to 0. And so that's how you finish solving this thing. That's for like a little dropped wire frame, feeling this syrupy drag force from the magnetic force that's going to be resisting the motion.